Thank you, Rich, and it's great to be speaking to all of you. As Rich mentioned, I'm new here as well. In fact, I just came from the new faculty orientation meeting on the other part of campus, so I'm as new as it gets. I just want to say one thing. My PhD at Caltech was actually supported by Stanford's Global Climate Energy Project, and then I have came back to start my own research group here, so sort of come back to the mothership. So I'm going to talk to you about energy conversion at elevated temperature. So this will be slightly different than what Paul talked about, which is a room temperature approaches for energy conversion. And I'm going to try to tell you some of the benefits and challenges that we're facing now and what type of research opportunities we have. So you've heard this probably throughout the week, but I just want to reiterate the overall vision we have is to have energy when and where it's needed. And my research focuses on converting energy between sunlight, electricity, and chemical fuel. If I were to highlight this energy conversion scheme, we have basically starting with the solar resource, we can convert that to a variety of chemical bonds such as hydrocarbons or hydrogen, and then we can subsequently combust them in a very efficient way, for example, using fuel cell and generate electricity and produces water and CO2 as the product, and that comes back forming a closed loop cycle. There's also a lot of research going on, including my group, looking at direct conversion to electricity and storage of electricity in batteries. But today I'm going to focus on conversion involving chemical bonds from sunlight into electricity. So one of the challenges when you have to deal with chemical, so for example, hydrogen or hydrocarbon, is that usually involves precious metals. And the reason is that it happens that the rarest metal on the planet are also the best catalyst for facilitating these conversion reactions. So this is the abundance table. The reference point is silicon, which is 10 to the 6th here. Some of the most common catalysts include platinum, iridium, ruthenium, rhodium. They're on the very, very lowest part of this diagram, right here in the rarest metal section. Some interesting fact about some of this material. There's 1 gram of platinum for every kiloton of sand, so that's pretty rare. 93% of the US platinum is imported, and 80% of the world reserve is in one mine in South Africa. You might have heard there's actually some there's problems at the mine. So this is a geopolitical issue as well. And if we were to take all of the platinum in the world and then convert that, and then use that to convert American cars to fuel cells, okay, at the current efficiency and utilization, that's all we can do, and then we'll run out of platinum. So obviously we need to look at better ways to reduce the use of platinum or even eliminate it or improve the efficiency of the catalyst to reduce the amount. So the title of the talk was elevated temperature. I'm going to try to convince you that by increasing the temperature from ambient room temperature to several hundred degrees Celsius, we can dramatically enhance the activities of catalysts and speed up chemical reactions so that we can convert these, so we can perform these chemical reactions more efficiently. So here is sort of freshman chemistry. You have on the y-axis energy barrier, energy coordinate, and the x-axis is the reaction coordinate. So a chemical reaction, for example, dissociating water or burning hydrogen goes from left to right. So it's downhill, so which is good. For some of the reactions, like burning hydrogen, for splitting water, it's uphill. But there is usually a very big bottleneck. This is called an activation barrier. So let me just give you a very quick example. If the barrier is 1 electron volt in magnitude, so this is the typical barrier for breaking most bonds, if we increase the temperature from room temperature to 400 degrees C, we will have a 1 billion times increase in the reaction rate. So this is a very substantial way to improve the reactivity of catalysts. So today I'm going to talk about 2 areas of my research. Number 1 is talking about making solar fuels with concentrated sunlight. And the second part is utilizing that fuel to produce electricity with solid oxide fuel cells. So you can see on the left here, we are making hydrogen or hydrocarbon, and then we're making water and CO2 and then feeding back. So this is a good example of a closed loop energy cycle. So why dissociate water at elevated temperatures? I already talked about the benefit of increasing the rate of chemical reactions, but there are also other results that follows as well. So here is the solar spectrum in terms of the power versus the wavelength of light. So the whole thing here is essentially your visible and non-visible infrared part of the solar spectrum. If we have a semiconductor material, say like iron oxide, we have a band gap, say about 2 electron volts. This is the part of the solar spectrum that can be absorbed efficiently, okay? Everything else is essentially lost as heat or not absorbed at all. So we're only utilizing a very small portion of the solar spectrum. So, but I talked about temperature. So actually, we can find ways to absorb this energy that was not used to generate electricity with the photovoltaic process and turn it into heat. And when this is concentrated, this naturally just heats up the material. So in a conventional PV, for example, when we shine concentrated light on it, it actually heats up and we have to spend work to cool it down. It's actually a major challenge with concentrated photovoltaic. But here we embrace the heat and we use this to speed things up. So this one aspect. The other aspect is if you look at the thermodynamics of splitting water. So if you want to take water and turn that into hydrogen and oxygen, there is a thermodynamic cost to be paid. And at room temperature, that cost is about 1.2 volts. But as it turns out, if you increase the temperature of the reaction, you reduce the amount of free energy that is needed to split water. So it actually goes from about 1.2 volt at room temperature, and that goes down to about 1 volt at 600 to 800 degrees Celsius. So you gain a 20% thermodynamic efficiency, but you also get much more by using this to speed up chemical reactions. And let me say one more thing for those who might not be familiar with the temperature effect on chemical kinetics. So essentially what we're doing is we are making the atoms vibrate more vigorously. And this allows it to have greater probability of hopping over a particular barrier. So this is really the thermodynamic and the kinetic argument for increasing the temperature of water dissociation. And as you can see, we have a better chance at utilizing the available solar spectrum. So to use high temperature, this is not trivial because most of today's PEC photoelectrochemical cells operate with in either aqueous system and usually operating with liquid water. So we have to think about how to convert this device so that it can operate above the boiling temperature of water, which is 100 degrees C. So how do we operate at 400 degrees? We have to transform this liquid-based cell into a solid-based cell. And that's exactly what we are trying to do in my lab. We're trying to take the approach at the left, which I think Paul talked a little bit about, where you have, say, nanowires for absorbing light, and you have a solid membrane, such as a polymer electrolyte membrane for carrying the hydrogen, the ions and protons and so forth, and running the circuit. But now can we replace the solid electrolyte, the liquid here, with a solid? And that's what we're doing here. Imagine you take out the liquid and you coat it with something else. Something that conducts protons, something that conducts electrons and holes. And that's what this device does. You can see here, we still have the same light absorber just like the left side, but now it's being coated with a film of something else, what we call a mixed conducting oxide. So if you follow the reaction that occurs here, you shine light, you form an electron hole pair. This electron hole pair, the hole travels very quickly through this material and reaches the gas. So this is the steam that's outside at several hundred degrees Celsius. And then the chemical reactions occur at the surface and you guide the proton down along the thickness of the shell across the membrane to the other side where hydrogen comes out. So it's a fully solid state device. There's no liquid involved. There's reduced corrosion problem. There's still some corrosion problem with the gas, but much less in the liquid case. And it's potentially more efficient because we're utilizing the energy that is otherwise have to be taken away to cool down the device. So this is a potentially interesting way to develop a new class of cell. Now, let me say a little bit too that because this requires concentrated solar power, if you just put the cell under sunlight, it's not going to get very hot. So we need to concentrate the sun by 100 or 200x. So this most likely will be for stationary applications where you have megawatt of power plant, maybe in the desert, in the Sahara Desert, in southwest United States, or elsewhere, whereas the room temperature will most likely address a smaller, more distributed, for example, on your roof. So this really targets a different strategy. These are some simulations we have run on the possible efficiency of our cell. In this contour plot here, the color represents efficiency, so red is about 30% efficiency and blue is 0. Going from left to right, we are changing what's called the band offset. This is the difference in the conduction band or the valence band offset between the two materials we were shown earlier, between the absorber and that mixed conducting oxide shell. So this is how much energetic barrier there exists. So you need to spend a little bit of energy to take the electron or the hole across. On the left side is the doping level in the absorber, where we have assumed a silicon-like material. The reason why you need to have higher doping level when you increase the temperature is because when you increase temperature, you form intrinsic carriers in silicon. And soon enough, you won't be able to generate voltage because you're just going to be at 0 volt when you shine light. So we need very, very high doping level. And this has some consequences as well, because when you dope higher, you will have problems with the mobility and scattering of the electron holes. But we've taken all this into account. It turns out that on the most optimal case, where you have a very small band offset, so a very small barrier between the two materials, and a fairly high doping level, it's possible to achieve a very high efficiency, about 30%, when you have a band gap about 1.6 electron volt. And when you operate at about 500 degrees Celsius. This is a very attractive temperature because it's not so hot, so we can still use an expensive material like stainless steel. But it's high enough so we can speed up the reaction. So you can see when we lower the temperature, the efficiency drops rapidly. So this is one aspect. So the way we will deploy it, as I said, is with a large field of mirrors or some sort of other configuration of optical concentration. Again, this is for large-scale megawatt production of hydrogen or beyond hydrogen. We are also looking at making hydrocarbons. We're looking at dissociating carbon dioxide into carbon monoxide, and so forth. But the challenges we face today are the following. Same with a room temperature photovoltaic process, we have problems with charge separation. The carriers like to recombine, and when you go to higher temperature, the interface quality may not be as good as the low temperature, but that's one area we're looking at as to how to have good charge separation. Stability at high temperatures is another problem. When you get too high, materials tend to fall apart, thermal expansion mismatch tend to destroy the device. So this is another challenge, but we are looking at this as well. But the most important part, as a material scientist myself, we need to find materials with the right properties. So I showed you a simulation earlier with various material properties that is desired. So now it's actually finding the right material that exhibits those properties. So that's the first part of my talk. The second of my talk, so now we have made the hydrogen, supposedly we're successful. So hydrogen, we can use them in the car and so forth to propel some sort of a combustion process, but it may be better to use the form of electricity, for example, to power our computers or coffee makers. And the way to do it is to use a fuel cell, which is a controlled combustion of gases. So we can throw hydrogen and oxygen together, light a match, and we'll go boom. Okay, so it's not a very efficient process, and you tend to create a lot of nasty byproducts like nitrous oxide, sulfur oxide that goes into the atmosphere. This is ultimately a problem. But if we do it controlled fashion, so basically we're bringing the oxygen one molecule at a time, in a controlled fashion, to the hydrogen and burning it. And this is an example of how a solid oxide fuel cell works. This, again, on the high temperature theme of my talk, focuses on fuel cells that work at temperatures significantly above ambient. So here, the fuel cell composed of 3 components. The first component is the electrolyte. So this is something that conducts only ions, but not electrons, and is impermeable to gas. And this actually physically separates the fuel, say hydrogen, and the oxygen. And on each side, you need electrodes. These are materials that would catalyze the reaction and facilitate the transfer of electrons. So on the fuel side, we have a fuel electrode. So in the fuel cell, this is called the anode because of the direction the electron transfers. So we have hydrogen reacting with oxygen ion that's coming through from the other side, producing water and then electron. And this electron goes to the outside circuit, powering some sort of a device. On the air side, we have the complementary reaction, which is the incorporation of air. So you take air, you bring that electron back, you combine it, you form an oxygen ion, and you push the oxygen ion through the electrolyte. You might ask the question, well, how am I going to keep the fuel cell hot? You talked about operating at high temperature. Well, it turns out this reaction is exothermic. So we actually don't have to do very much. In fact, most fuel cells suffer from the problem of being too hot. So this naturally can run in a self-sustained manner. Once you ignite the reaction, so to speak, like an engine, then it would just run by itself in terms of thermally self-sustaining. So this is good. And this is already commercialized. This is a GM fuel cell on the polymer electrolyte side. So this is the room temperature. On the left is actually right here in Silicon Valley. It's known as the Bloom box. You might have heard about it. It's the one of the massive manufacturing exercise at making solid oxide fuel cells, and they've been deployed several tens of megawatts of capacity around the world. So, but despite these challenges, there are still much to do. Sorry, despite the success, there's much to do. So the problem is some of the fuel cells are too cold, and some of the fuel cells are too hot. So the GM fuel cell I showed earlier runs at about 80 degrees Celsius, so it's pretty cold. Okay, but there's some benefits. It's very inexpensive on the system component because you can use inexpensive material to hold the fuel cell together. It's very reliable because you don't have to go to very high temperature, and it starts instantaneously. This is why they use in automobile applications. On the Bloom boxes, it's on the high temperature side. So it runs at about 800 degrees Celsius. That's pretty hot. So you have all these problems. It's expensive because you have to have very expensive enclosure to hold it in. It's less reliable because the material tends to degrade, and the startup time is very slow. But of course, at the high temperature, we have the following benefits. The reactions, as I said in the first slide of my talk, it's very, very fast. It's enormous. You don't even need platinum. Right? So what we want is to have the best of both worlds. We wanted to have the advantages of the high temperature and the advantage of low temperature. So it turns out we need to operate somewhere in between. And the type of materials that my group is interested in, we're looking at material that can work at about 400 to 600 degrees Celsius. So this is the range where you can still use stainless steel as an enclosure material, and you can still leverage all the benefit from accelerated reaction kinetics and lessening the requirement of precious metal catalysts. And some of the material we're looking at are fast oxygen ion conducting materials. So these are oxides that you can take oxygen ion through very quickly. We're also looking at a proton conducting oxide, which is the ceramic analog of the polymer electrolyte. So here you don't need the water to carry the proton, but the proton is in a purely solid state manner. So essentially it's proton hopping from positions within the material from site to site. So this is some work I've done in the past. We actually show it's possible to eliminate metal altogether when we go to this higher temperature. So for example, we were looking at a material known as cerium oxide, which is already known as a good catalyst for fuel cells. But we did actually a very simple experiment. We wanted to know exactly how active cerium oxide is relative to platinum, one of the best catalysts. So what we did was we used lithography, and we made very well-defined features of platinum on cerium oxide. Okay? So you have a surface like this. You have platinum features on cerium oxide, which is a catalyst, and you have hydrogen around and water around on the gas right above the cell. What is very strange is that when we change the amount of platinum on the surface, so we made very, very small platinum or very, very large platinum, so essentially changing the available reaction sites, we actually saw that there was no change in the activity of cerium oxide as a catalyst. So we immediately confirmed that platinum was much worse than cerium oxide when it comes to high temperature catalysis. This is very interesting because traditionally you have thought, well, how can anything be really better than platinum? So not only is better, it's also more abundant. Cerium oxide is almost as abundant as copper itself. So this is a pretty good material. So this really illustrates the benefit of going to high temperature and what it can do for chemical kinetics and at lessening the requirement of precious metal. So we actually made a very nice, elegant nanostructure from this. So typically in the past, for polymer electrolyte fuel cell, we tend to optimize the amount of surface area carried by the platinum. So we made really, really small platinum nanoparticles on the order of 10 nanometers or less. But it turns out that we can also do the reverse. Rather than optimizing the metal, we optimize the ceramic, the oxide. So we actually grew nanowires of cerium oxide, and we showed in this plot here on the y-axis is activity higher is better, and the x-axis is inverse temperature. In red is this what we call the nanocolumnar cerium oxide. It's actually better than any of the other catalysts which has nanostructured materials like platinum, nickel, ruthenium, rhodium, and so forth. So even without any metal, it's 1 order of magnitude better. So this really, again, shows the importance and the benefit of going to high temperature. But, of course, we're not stopping here. There's still much not known about these materials, and the problem is the lack of fundamental understanding. If you take a look at the reactions that take place, on the area electrode, you have a 4-electron process to take oxygen, combine it with electron, turned into oxygen ions. At the fuel electrode, you have a 2-electron reaction, potentially simpler, but it's actually very complex as well. But if we want to use natural gas, the US has a huge reserve of natural gas, it makes sense to find a way to more efficiently utilize natural gas. It's an 8-electron process, increasingly more complicated, and really nothing is known. And what we want to study is, if we were to zoom in into the catalyst, on the very surface that it intersects with the gas, with the hydrogen, the methane, and so forth, what happens there? What is the atomistic picture of what's happening? And this brings me, with great excitement, to tell you the type of collaboration we have at Stanford and beyond. At Stanford, we have several outstanding resources that's really only available here, and actually our location in the Bay Area positions us to use some of the best facilities here in the world. We're using very intense light, specifically X-ray light, to look at these chemical reactions at the Stanford synchrotron light source, just a mile from here. I think many of you have visited earlier this week. We're also using the Advanced Light Source, which is another synchrotron facility located at Lawrence Berkeley National Laboratory, about 50 miles from here. And we're also using the Stanford Nano Center, which has some very powerful characterization technique. I'll talk very briefly about them just now. The couple of techniques we're applying are as follows. We're applying what's called ambient pressure X-ray spectroscopy. So some of you may know that spectroscopy is typically done at very low pressure, like 10 to the minus 9 torr. And the reason is because electrons scatter very easily, so you cannot have a lot of gas there. But along with scientists at SLAC and at Lawrence Berkeley National Lab, we're now developing special apparatus that can operate at pressure as high as 100 torr. That's higher than 1/10 of an atmosphere. So we have essentially a 10 order of magnitude increase in the operating pressure of spectroscopy techniques. So this is very interesting because now we can actually put in the hydrogen, we can put in the water, we can put in the methane, and we can see what happens to the electronic structure of the surface as the reactions take place. The second technique that we're applying is called surface X-ray scattering. This is mostly done at SLAC. So we are shining X-ray light, and using a special technique called crystal truncation rod analysis, we can actually focus onto the top atomic layer of the catalyst. The very, very top, the atoms that intersect with the hydrogen, with the hydrocarbons. What does it look like? What is the structure of the material? And this is allowing us to look, again, not under static conditions, but under dynamic conditions. Finally, we're also applying what's a conventional technique, but taking it one step further. Transmission electron microscopy is a great way to get awesome resolution. You can get sub-nanometer resolution, you can see atoms, it's great. But again, most of the time it's done in vacuum. So chemistry can't really take place. But we at Stanford, at the Stanford Nano Center, have a very nice instrument called the environmental TEM. And this allows us to run reactions on the order of 20 millibar. So again, we can put in all the gases and watch with atomic resolution what is happening to the materials. So I feel I'm running out of time. So let me conclude. If you didn't follow any of that talk, I apologize. But let me repeat the take-home message. Elevated temperature process will play a crucial role in solar to fuel and fuel to electricity conversions. And I want to acknowledge my group. Although I've only been here a couple months, we have now assembled, I think, a great team of people working at these problems. A lot of the computation was done by Xiaofei Ye, who is a material science graduate student, and Albert Feng, who is in the applied physics department. In addition to this, we're also looking at other electrochemical processes such as energy storage in batteries and catalysis, and have the pleasure of working with some of the top faculties at SLAC at Stanford, such as Nick Maloge, Ziek Shem, Mike Toney, and so forth. So I want to thank you for your attention, and I'm happy to answer any question you have.
On one of your slides, you showed the transition from using water in your fuel cell to strictly solid. Correct me if I'm wrong, but if you do that at higher temperatures, the water doesn't evaporate away?
Sorry, say the question one more time.
One of your slides showed
This one?
two different, no, this is way back.
Way back?
Two different solids,
way
one
back.
with water and then one with strictly solid. Now, did you do that in order to be able to transition to the higher temperatures so the water wouldn't evaporate?
Oh, you mean the solar fuel?
Yeah.
Oh, I see.
That-
Yeah. So if you want to operate above 100, the water will be steam.
Have you considered pressurizing it?
That is a good point. I don't remember the phase diagram very well of water, exactly how much pressure is needed to maintain a liquid form. So I can't answer that question, but operating under extreme pressure is a challenge in itself, I think. So we definitely want to operate at ambient pressure, at 1 atmosphere if possible, but we can of course go a little bit higher. Yeah, but that's a great question. Yeah.
Do you have challenges with reaction efficiency because of sort of just the motion of molecules in gas phase?
The motions you're talking about how fast gas molecule diffuse.
That and just the fact that you won't have maybe as much continuous contact with your electrodes as you would if you had one.
That is an excellent question. So to answer the first question, gas diffusion is very, very fast. So it usually is not a problem to bring gas from one place to another, the gas molecules. The second question is very good because in the liquid system, the ions are everywhere, the protons are everywhere. But in the solid state system, we have to bring them in from these sort of thin devices. So the conductivity becomes a problem. So yes, that is a challenge because you can reach every crevice very easily here, but it's much harder in the solid state case. So that is one of the price that we pay. But we are finding material, this is why it's called mixed conducting. It conducts all the species you need to in one place, so you don't need to find two materials that does each one of them and then trying to put them together. It would be very difficult, for example, if you just had one material that conducted proton and one material that conducted electrons. Then you would only conduct both things, which is what you need at an interface. And having those junctions is very, very difficult. Yeah. So I think we're trying to address that as well by using a material that conducts all the species we want. Yeah. Yes.
Do you have a promising material that
We have quite a few actually. So my students are now testing them. We have gotten some preliminary efficiency number. They're not terribly good, and the reason is we haven't started making these wires. So for now, for simple experiments, we're just using a planar geometry, just like a thin film geometry, so it's very low surface area, just to get a sense of what it can do. But we are looking at several materials for the absorbers. It turns out that hematite, which is iron oxide, is one of the most abundant material. It's very inexpensive, and it's a great light absorber in the 1.6 to 2 electron volt band gap that we need. So that's one material we're looking at. For the coating, which is another crucial part of our device, we're also looking at several ceramic materials such as barium zirconate, which is known to conduct protons well, and we are modifying it so that it can also conduct electrons. So yes, so we're looking at that quite a bit. Yes, in the front.
I was just curious to know how you plan on sustaining. You mentioned two processes, one at 450 degrees Celsius, one at 600. I was interested in how you plan on sustaining that high temperature for a prolonged period of time, because I feel like that would require a lot of energy to do that.
That is a good question, and actually it turns out in the case of solar fuel generation, operating with concentrated solar is done. People are doing every day. There are huge tens of megawatt plants in the desert now. So by tracking the sun and concentrating the solar radiation in one place, you can actually maintain high temperature very easily. In fact, the temperature we're asking for is low. It's very easy to get temperature. So for my PhD work, we did solar concentration up to 1500 degrees Celsius. And just by pointing mirrors and putting in one place. So it's actually, we are leveraging the existing development in the concentrated solar power industry. And that's, I think is a good link, so we don't have to pay the price to develop those. And Nick, who will speak after me, will also talk about concentrated solar applications as well. Yeah. One more question. Yes.
In the slide you had on the cerium oxide catalyst compared to the efficiency of platinum, under the cerium oxide there was a layer of yttrium or zirconium oxide. Was that just like a substrate for layering cerium oxide, or did it have a separate one?
that is actually the electrolyte. So that is something that conducts only the oxygen ion, because cerium oxide conducts both electrons and ions. So if you were to not have this layer, the whole cell was short. Yeah. So that's just the electrodes, the same as the liquid for conducting protons in the photoelectrochemical cells. So thank you, everyone. Enjoy the rest of the event.